Good day, everyone. Today we will be discussing Experiment 1, the recrystallization of acetanilide. But first, allow us to give you a brief background of this experiment as well as some key concepts and theories behind it. The purification of organic compounds is a vital part of organic chemistry. In synthesizing compounds, it is important that the starting materials are pure and free of impurities. One way of removing impurities is recrystallization. Recrystallization is a common technique used to purify solids and it is based on their varying solubilities. Thus, it is important to pick the right solvent. The compound that will be purified is acetanilide, a synthetic organic compound with various uses. In this experiment, water was used as a solvent as acetanilide is soluble in water at high temperatures and insoluble in low temperatures. A compound is considered impure if there are minor components of another compound mixed in with it, or when there is a mixture of two or more components and only one is desired. When an impure compound is dissolved at high temperature, it makes a highly concentrated solution. After the solution is cooled, the compound is no longer soluble in the solvent and so it crystallizes. The impure substance, which in our experiment is acetanilide, then crystallizes before the impurities, leaving the impurities behind in the solution. We also use activated charcoal in this process to remove any colored impurities, which are usually polar organic compounds with an affinity for activated charcoal. The melting point is also a physical property that is used for the purpose of determining purity. A pure substance would have a higher melting point compared to an impure substance, and thus the melting point analysis helps confirm the purity of the substance.
Moving on with the method of the group in performing the recrystallization of acetanilide. Once we had prepared the needed glassware, the group started the setup. Figure shown in the screen is the filtration using a fluted filter paper. The group weighed 1 gram of impure acetanilide and placed it in an Erlenmeyer flask. Beforehand, we recorded the actual weight of it, which is 1 gram. We then added distilled water. While heating, we placed a pinch of charcoal until the solution was clear. Continue to stir it until boiling. Then the other members can prepare the filtration setup by folding the filter paper and placing it in a funnel. Erlenmeyer flask would be the receiver for this setup. Preheat the setup just prior to use by pouring hot solvent into the filter paper. If the filtrate remains to be color, add a pinch of activated charcoal and heat. Refilter by gravity filtration, cool slowly to room temperature and observe the appearance of crystals. To induce crystallization of more acetanilide, chill the flask in an ice water bath and scratch the walls of the flask. Assemble the suction filtration apparatus. Determine the weight of the filter paper, in our case it was 0.6 grams, and place it in the Buchner funnel. Fit the funnel to a suction flask. When the suction filtration apparatus has been set up, moisten the paper in the funnel with few drops of the solvent. Now, filter the crystals out of the solution by pouring it in the funnel. When the crystals are almost dry, release the vacuum by disconnecting the tube from the suction flask and wash the crystals with 5 to 10 ml of cold solvent and use a stirring rod for half a minute. Reconnect the tube to dry the crystals. To dry the crystals, the group transferred the crystals together with the filter paper into a watch glass, covered it with another filter paper and kept it in the locker until the next laboratory period. Weigh the dried crystals and filter paper to the nearest 0.01 gram. At the end of the activity, the group determined the percentage of the pure crystals recovered from the impure sample.
The results were obtained on the following laboratory class schedule, which was 2 weeks from the actual day of experimentation. For the results, it was found that the mass of impure solid acetanilide was at 1 gram. The mass of the empty filter paper was at 0.6 grams. The mass of the empty filter paper plus the recrystallized solid of the final product was found to be at 1.13 grams. To compute for the mass of purified solid, we have to subtract 0.6 or the mass of the filter paper from the mass of the empty filter paper plus recrystallized solid, which was found to be at 0.50 grams. And then the percent yield was computed when we divide 0.50 over the mass of the pure acetanilide, which was 1 gram, multiplied to 100, which we got was 50%. The melting point of acetanilide was found to be at 114.3 degrees Celsius, but the melting point of pure acetanilide was at 150 degrees Celsius. Why is that? It's because when a substance melts, it doesn't happen exactly at the same temperature as its pure form, because the process isn't perfectly balanced. However, the temperatures are usually very close or usually less than a degree Celsius of um differences. Acetanilide has a lower melting point when it has impurities mixed in, but when these impurities are removed by boiling, acetanilide becomes pure and the melting point becomes high. A solid with impurities that dissolve easily tends to melt at a lower temperature compared to pure substances. This happens because when a substance melts, it needs energy to break the forces holding its molecules together. The stronger these forces are, the higher the melting point. In the in this case, pure compounds would have a stronger force holding their molecules together. Alongside, impurities in a solid disrupt the regular pattern of these forces that hold the solid together. This disruption means it takes less energy to melt the parts of the solid near the impurity, thus a lower melting point. Some guide questions were also answered to further understand the experiment. First question was, among the following solvents, which one was observed to be more suitable for recrystallization of acetanilide? So water is highly polar, which makes it a poor solvent for nonpolar compounds like acetanilide, especially at low temperatures. An ideal crystallization solvent should dissolve the compound of interest, such as acetanilide, at high temperatures to allow impurities to dissolve, and then allow it to crystallize when cooled out when it is less soluble. Second was, why was a water bath used instead of direct heating in the choice of solvent? This is to maintain uniform or constant heating of the solution, and it is the preferred heat source for flammable chemicals to prevent sudden ignition with indirect conduction. Third was, why was an activated charcoal added into the mixture of acetanilide, sodium chloride, and Congo red? What is absorption? So activated charcoal is used in recrystallization primarily to absorb colored impurities from the solution. It works by having a large surface area with many adsorption areas, which means that adsorption is a process where a solid is used for removing soluble substances from water that can trap molecules of impurities, particularly those that have colored ones or similar polarities to activated charcoal. Next is, why would it be wrong to dissolve the original impure material in a large excess of solvent, and why? Yes, because much solvent will prevent the compound from recrystallization, therefore no yield of crystals. The fifth question was, in gravity filtration, what is the advantage of using short stem funnel over a long stem funnel? Using a short stem funnel would minimize the presence of premature crystals that can form on the stem of the funnel. For the sixth question, why were the funnel and the flask preheated before filtering the impure acetanilide? It is important to keep the gravity filtration setup warm to prevent premature crystallization in the stem of the funnel and in the filtered paper. As hot solution passes through the filter funnel and filter paper, it cools down. If the filtration setup is not kept warm, the temperature drop can cause the compound being filtered to crystallize out prematurely. Seventh, why was the filter paper in the Buchner funnel melted before pouring in the mixture contained the acetanilide to be crystallized? This is so that the filter paper adheres to the funnel and creates a seal that the crystals can't pass through. And number 8, what is the purpose of washing acetanilide crystals with a few milliliters of cold solvent? What do you think would happen if the solvent washing was not cold? So the primary purpose of washing the cold solvent is to remove residual impurities that may adhere to the surface of acetanilide crystals, since some impurities may remain trapped or absorbed on the surface of the crystals despite the purification step. Also, using a cold solvent would keep the crystals from melting.
For number 9, why must the rubber tubing of the suction flask be disconnected before turning off the aspirator? This is important to prevent potential backflow of water or contaminants into the filtration apparatus. For number 10, why is it necessary to have thick-walled tubing in connecting the suction flask to the aspirator? This is because the tubing must be thick enough to withstand the suction pressure, as thin-walled tubing would collapse under the suction. For number 11, at what steps in the recrystallization procedure did you lose some of the product? What can you do to prevent future losses? So, there was some loss of product when the activated charcoal was added. As charcoal absorbs the impurities, adding too much absorbs some of the acetanilide as well. To prevent this in the future, it is important to add an adequate amount only. As for number 12, what is the effect of impurities on the observed melting point on acetanilide? So, impurities typically lower the melting point of acetanilide. This phenomenon is known as the melting point depression. When impurities are present, they disrupt the regular crystalline structure of the acetanilide molecules.
An ideal recrystallization solvent should dissolve the compound of interest at high temperatures and then allow it to crystallize out when cooled and less soluble. Thus, the best solvent for acetamide is benzene because it is soluble in hot but semi-soluble for cold for it is to crystallize, and water for aspirin because it is soluble in hot but insoluble in cold temperature. Acetamide and acetanilide share comparable polarities and solubilities in water, making their separation through water recrystallization hard. Due to their similar properties, both compounds would dissolve in hot water and are likely to crystallize together upon cooling. This process would yield a mixed or impure final product rather than having pure crystals of each compound. Aspirin and acetanilide can potentially be separated by recrystallization from water. When the hot solution with both compounds is cooled, aspirin, which is slightly soluble in cold water but highly soluble in hot water, would crystallize out. In contrast, acetanilide, being soluble in hot water, would remain dissolved in the solution. This difference in solubility behaviors allow for the separation of aspirin from acetanilide during the recrystallization process. For the recrystallization scheme, dissolve the mixture, aspirin, acetamide, and sample Y in hot water. Aspirin will be the most soluble component in hot water. Filter the solution to remove any insoluble impurities. Allow the solution to cool slowly. And as the temperature cools, aspirin will precipitate out of the solution due to its lower solubility in cold water. Next, filter the cold solution to collect the purified aspirin crystals. Finally, the liquid left over after filtration may contain acetamide and sample Y. You can evaporate the filtrate to dryness to recover any remaining acetamide or sample Y, but it is unlikely that you will be able to separate them from each other using this method.
And that is all for our report. Thank you so much for watching.